Have you ever wondered how fluids work? Did you know that there's actually an equation out there that can tell you how fluids move? This equation is called the Navier-Stokes equation, and we're gonna derive it together.
So first, we start out with Newton's second law of motion. Force equals mass times acceleration. And we'll apply that onto a very, very small fluid element. It's so small that it has dimensions dx, dy, and dz. That means that's really, really small. And with those dimensions, we can therefore express the volume of this fluid element as dv equals dx, dy, dz. Now let's go back to our equation. With F equals ma, we need to find a way to express this fluid element in terms of mass. We already know how the volume of this fluid element can be expressed, so let's use that to find mass. Since density is mass over volume, and we know that volume is dV, we can therefore express mass as density dx, dy, dz. So that's the mass part of the equation. But how about the acceleration? Now, acceleration can be written as dv over dt, or the derivative of velocity with respect to time. And using chain rule, this can then be written out as the partial of v with respect to t plus dx over dt partial of v with respect to x plus dy over dt partial of v with respect to y plus dz over dt partial of v with respect to z. However, note that velocity can also be written as the derivative of r with respect to time, or how position changes with time. And this can then be written as dx over dt, dy over dt, and dz over dt. This is just how it changes in those specific axes over time. From there, we can plug it into our first equation for dv over dt, thus giving us partial of v with respect to t plus vx partial of v with respect to x plus vy partial of v with respect to y plus vz partial of v with respect to z. But note that this whole thing can just be written as v dot del of v. So that's our acceleration, so let's write that down. I'm just going to number that so we don't get confused. And that's how you get mass and acceleration. But now let's look at the forces acting on this fluid element. So here we have our fluid element. There is pressure acting upon this fluid element. Let's look at it on two faces. First, let's take the left face located at x. Pressure acts perpendicularly to the surface, and on the leftmost face, it's pushing to the right. And therefore, we can say that the pressure acting upon the left face can be written as P of x, and the area of this face can be written as dy dz. Now let's look at the right face. We do the same thing, but notice that it's located at x plus dx. Therefore, using the first Taylor expansion, we write the pressure on x plus dx as P of x plus partial of p with respect to x dx. And since this time, the pressure is moving to the left, it's in the negative direction. Taking once against the area, you multiply it by dy dz. And then we add the forces due to pressure on both of these faces. And after cancelling out p of x, we are left with negative partial of p with respect to x dx, dy dz. So let's just write that down again. And note that this fluid element is in 3 dimensions. So pressure is not just working on the x-axis, it's also working on the y and z-axis. So let's do the same procedure for y and z. Add them all together, and we get the final expression for the force of pressure on this fluid element, which can just be written as negative del p dv. And that makes our second equation, which is also the first equation for force acting on our fluid element, the force due to pressure, which is negative p dv. However, pressure is not the only force acting on our fluid element. There is also an internal friction within the fluid, which is known as the viscous force. So now, let's solve for the viscous force. So we know that for a Newtonian fluid that has a constant viscosity mu, the shear stress component acting in the I direction on a surface perpendicular to xj is given by tau ij equals the constant viscosity mu multiplied to the quantity of the partial of vi with respect to xj plus the partial of vj with respect to xi. And you can get the force per unit volume from viscosity with the divergence of the viscous stress tensor, which is given as such. However, we already know what tau ij is, so we can just plug that in. And once you distribute terms, you end up with this equation. Now, the first term is equivalent to the Laplacian of the ith component of the velocity vector, or del squared v sub I, while the second term is basically just the partial derivative of the divergence of the velocity with respect to x sub I. However, we also know that for an incompressible fluid, the divergence of v is just equal to 0. So plugging this in, that cancels out the second term, and we're left with the viscous force being mu times del squared v. And now we put that down as the next force that affects our fluid element. And finally, we have the effect of gravity acting on the fluid element, which could simply be written as rho g dv. So we've got our mass, our acceleration, and our forces. So we just put it all together, divide everything by the common dv, and we have our Navier-Stokes equation.
And that's how you derive the Navier-Stokes equation. So remember, if it flows, Navier-Stokes knows.